Geometry class. In chapter 3, we kind of got away from doing the proofs and stuff for a little while, but sad to say that in chapter 4 we are going to get back into that. I make sure that you guys all have a green sheet. I made them green this time around. I think they were purple last time around. So make sure you have a green sheet. We're going to have um, four theorems or postulates to fill in today. Um, so make sure you have that handy. Section 4.1 um, does have a proof in the notes for it, but I don't think it has a proof in your homework assignment. So you'll get one more day of freedom for now. So 4.1 just talks about angles of triangles, and for the most part, it should be pretty basic. It should be kind of stuff that you already know. So the first theorem just basically says that the angles in a triangle, angle A, angle B, and angle C, they have to add up to be 180 degrees. So all three of those inside of there add up to 180, and that can help you solve for one of them. If you have the other two, you can find the third one. What I want to do is go a step further and show you why that has to be 180 degrees, though. And I'll draw it over here, I guess. If you have a rectangle, a lot of you guys might know that that's 360 degrees, but a triangle is just half of a rectangle. So if I split that 360 degrees in half, that just leaves 180 degrees inside of a rectangle. So pretty basic. That's the explanation for why a triangle has 180 degrees inside of it, okay? So let's go ahead and add that to our sheet here. This is theorem 4.1, so I'm going to put THM 4.1, okay? Make sure you label it THM because some of them are postulates, some of them are theorems. We're also going to deal with a different type than even postulates and theorems today, so make sure you label that. This is the triangle angle sum theorem. I'm going to abbreviate theorem. Triangle angle sum theorem. The meaning of it is I'm just going to put all angles of a triangle add to 180 degrees. Okay, and then I'm just going to draw a picture over here of, let's say, A, B, C, and so I'll say A plus B plus C equals 180. Just basically like that. If I'm going too fast on this, feel free to pause and you can finish writing those in there. So that's our first theorem or postulate. I'm going to go through the proof with you. It's kind of a long one, but you can kind of see how it flows really nicely. This is a 2-column proof again, so here is how we know that there's 180 degrees in a triangle. That wasn't just made up. It was proven from somewhere. In addition to the fact that it's half of a rectangle, they have proved it this way. So what we're given is we're given triangle ABC. That's all we're given, triangle ABC, and they have gone ahead and labeled angle 1, angle 2, angle 3, okay? And they want to say, hey, prove to me why angle 1 plus angle 2 plus angle 3 have to be 180. So that's what we're trying to get to, okay? So down here we start with triangle ABC. Well, that's what we're given. So I'm going to write in number 1, given. That's always the first step, okay? Then what they did for this guy is they drew really a line, AD, this line right here, through A that's parallel to BC, okay? They drew that line through there just to help us out because that's gonna get us to the next step. So that's something called the parallel postulate. And that's something that we don't use a whole lot. I wouldn't worry about trying to memorize that or anything, but that's the parallel postulate, okay? And then number 3, so after we've drawn that line, they're saying that angle 4, I'm going to use a different color here, angle 4, which is this guy, just that one, and BAD. BAD is like a combination of 2 and 5 together. It says that those two things form a linear pair because they're on that straight line. So this angle 4 plus this angle here, this one here, make up that 180 degrees, okay? And that is the definition, 1, 2, 3, definition of linear pair. Okay, by definition of a linear pair, we can see that those two form a straight line. Great, okay? And then it says, well, if they're a linear pair, then aren't they also supplementary? They add up to be 180 degrees? Yeah, they do. So we had a theorem or a postulate or something once that said that if It was a linear pair. I don't remember what the number of this one was, but it's back if you look on your purple sheet. If it's a linear pair, then it's supplementary. Okay, all linear pairs are supplementary, have to be. Okay. All right, so then they've gone a step further and they said, okay, since angle 4 and angle BAD are supplementary, we can just go ahead and say that angle 4 plus angle BAD is 180. Okay, if I add those two angles together, angle 4 and then this angle right here, they have to add up to be 180. Okay, and I'm going to do a different color again. This is number 5, and that is definition of supplementary angles. Definition of supplementary angles tells me that. Okay. All right, now they've gone ahead and they've said, well, angle BAD, the BAD that we were talking about up here, angle BAD is made up of angle 2 plus angle 5. Angle 2 plus angle 5. Those two angles make up BAD. Okay, and what we're doing here is we're adding two angles together. That is the angle addition postulate. I don't know what number that was, but we're just going to call it angle addition postulate. All right. If you look on your purple sheet, you can find it. All right. Okay, going back to the purple color, so we kind of have a little pattern going on here. It says that, well, okay, if I had up here that angle 4 plus angle BAD is 180, but then we say that BAD was 2 plus 5, we can put this 2 plus 5 in here for BAD. We're just replacing the BAD up here with 2 plus 5, okay? So now we have angle 4 plus 2 plus 5 gives me 180. Angle 4 plus 2 plus 5 gives me 180, okay? So what we've done there is just substitution. Okay, all right, now angle 4 plus 2 plus 5 is 180, okay? Then they're saying that angle 4 is congruent to angle 1. Let's locate, I'm going to use a pink color now. Angle 4 is congruent to angle 1. How can we say that 4 and 1 are the same size? Well, if you remember, this line here is parallel to this line here. So angle 4 and angle 1 are alternate interior angles, okay? And that's going to be the theorem that we've got going on here. Step 8, we can call those 4 and 1, and additionally 5 and 3 are also alternate interior angles. That is the alternate interior angles theorem that says that. Alternate interior angles theorem says that if they're alternate interior, they are congruent, okay? And now we go from being congruent to equals, okay? And that was just definition of congruence. Remember we had that weird thing before, definition of congruent. That goes either from congruent to equals or equal to congruent. And then we went ahead and said, okay, that means that angle 1 plus angle 2 plus angle 3 is 180, which is kind of like what we said up here. Okay, but this one we said angle 4, angle 2, and angle 5 are 180. Here we're saying 1, 2, and 3 are 180 because this angle 4 is being made and changed to angle 1, and angle 5 is being made changed to angle 3 because they're congruent up here. So basically what we did was we took angle 1 and slapped him in this spot, and angle 3 and slapped him in that spot. And that was just another substitution. We substituted 1 in for 4 and 3 in for 5. And here we have that angle 1 plus angle 2 plus angle 3 is 180 degrees. And that's how we know that there's 180 degrees inside of a triangle. Okay? All right, that was the longest part of this section. Now we get to the kind of funner stuff. Flipping out to the back side, we've got use the triangle angle sum theorem to find the measure of the numbered angles. So we've got angle 1 here, we've got angle 2 here, and we've got angle 3 here. Now, do not try to solve them in that order because you can't in this case. Angle 1, angle 2, and angle 3, it doesn't matter what order you solve them in as long as you get them solved. I'm going to solve them. I'm going to start with angle 3 here first, okay? I have angle 20 here, and I have angle 78 there, okay? But I know from the front side of the sheet that they have to add up to be 180 degrees. So if I add 20 and 78, that's 98 degrees. And if I subtract 98 from 180, that gives me, what, 82? Yeah, 82, okay? So angle 3, I'll put this all over here. Angle 3 is 82 degrees, okay? And all my scratch work will go over on this side, all right? Now let's go to angle 2 now instead, because I can't solve angle 1 yet. Angle 2, if you look across from angle 2, 78 degrees is across from it. So angle 2 and that 78 degrees, those are vertical angles. So vertical angles, I'm going to write that down so you can remember how we got that. Vertical angles, angle 2 has to be 78 degrees also, because vertical angles are congruent. Okay, and then angle 1, if angle 2 is 78, let's see, 78 plus 61 gives me 139. And if I subtract 139 from 180, that's 41. So angle 1 is 41 degrees. There we go. Okay, so just kind of mapping that around. We went in a different order, and that's a-okay. Now we're moving on to the exterior angle theorem. And this is something that you probably have never thought about before, but it just kind of makes sense, I guess. I'll look at this example over here, and I'll kind of put some numbers in here. What this, the exterior angle theorem says is this angle 4 that they've numbered right here. Angle 4 is going to be the same size as what would happen if you would add angle 1 and angle 3 together. So let's just slap some numbers in here. Let's say angle 1 is 40 degrees, angle 3 is 50 degrees, and angle 2 would then have to be 90 degrees, okay? In order for all of those to add up to be 180. Angle 2 looks like it's slightly larger than 90 degrees, but whatever. We're just putting some numbers on there, okay? So 40, 50, and 90 is what I have here, okay? Well, angle 4, since it's on the same line as what this 90 degrees is, that angle 4 would have to also be 90 degrees. And it's no coincidence that 90 degrees is the same as what 40 and 50 are added together. So these two added together make up the size of what the exterior angle is. So that's what this thing says. If I have angle 1, it's the same measure as what B and A are added together. Okay, if I just add those two up, it will be the measure of that exterior angle 1. All right, so let's write that on our green sheet here. I'll try and summarize that a little bit. This is theorem 4.2. The exterior, I'm going to abbreviate this, exterior angle theorem. Okay, and it says, I'm just going to say angle A plus angle B equals angle 1. Okay, and I'll just draw a picture of what this looks like. Maybe, oh my, that was really bad. That doesn't even look like a picture. Doesn't even look like a picture. That's okay. This is angle 1. This is angle, let's call this one angle A and this one angle B. So if I add angle A and angle B together, it makes, it's the same size as what angle 1 would be. Okay, mine doesn't look anything like the picture, but it's the same idea. So you can either draw this one or you can draw the one that's on the notes. Okay, either one will work. All right? Okay, pause if you need to. I'm not going to go through this proof right here, but it just shows you why this angle, angle 1, has to be the same size as the opposite two added together. It just shows you why that is, okay? So if you want to read through that, that is a flow proof, actually. But I'm going to move on to the next page. So they want us to use the exterior angle theorem to find out what x is and ultimately find the measure of JKL. JKL is this angle right here. And they've got kind of an algebra expression there for us. So 2x minus 15. So 2x minus 15, that is the exterior angle. Exterior means on the outside. And that exterior angle has to be the same as the two opposite ones added together. Okay. Well, the two opposite ones added together would be x and 50. So x plus 50, if I add those two together, that has to be equal to the exterior angle, 2x minus 15. Okay. Now, notice how we kind of neglect this 1 right here that's attached to the 2x minus 15. We don't even care about him in the whole equation. All we care about is the exterior angle and the two ones that it's not touching. Okay, we kind of totally neglect this guy. It doesn't matter. We don't care about him. Okay, so let's solve our equation here. I'm going to subtract x from both sides. get him to go away. So 50 equals x minus 15. Some of you guys do this in just one step, and that's fine. 65 is what x is, or should be, okay? But that's not what they're asking. They're asking for the measure of JKL. JKL is this exterior angle. Okay, they want that guy. And he is labeled by the 2x minus 15, so we're going to plug that back in. 2x minus 15, so 2 times 65 minus 15. Try to do some of this stuff in your head if you can. 2 times 65 is 130, and 130 minus 15 is 115 degrees, okay? There we go. That's that example. All right, and we have two more things that we need to write in our theorem postulate sheet, and these are actually called corollaries, is how that's pronounced, corollary. Now, I told you before about theorems and postulates and the relationship between the two. Theorems are like the big guns. Postulates are like the baby brothers. Corollaries are even smaller than that. So corollaries are like just really, really basic facts. Postulates are a step up from that, and then theorems are the big guys. So I don't know if we've had a corollary before, but we'll go ahead and write these down also. So corollary. I don't know how I want to do this. I'll just do this. So I'm going to call this COR, is how I'm going to abbreviate that. And this is COR 4.1 and COR 4.2. Okay? All right, so corollary 4.1. Let's read what it says. It says, the acute angles of a right triangle are complementary. Okay, here's what this means. Here's a right triangle, and this only works for right triangles. Right triangle. This is a right triangle. This is 90 degrees, okay? If an entire triangle is 180 degrees and 90 degrees is used up in this angle C, then that means A and B together have to be the other 90, right? So it's kind of like saying A plus B together have to add up to be 90. A and B are complementary. They add up to be 90 degrees, okay? So let's just write in here. This one doesn't have a name. Corollaries don't usually have names, so I won't put a name there. But for meaning, I'll put acute angles of, I'm going to put all caps, of right triangles are complementary. Okay, and here's my picture. I'll do a picture over here on the side. Here's C and A and B, and I will say A plus B equals 90. Okay, that just kind of gives me a shortcut. If I know what A is and I know that C is a 90-degree angle, I only have to subtract that A from 90 to get what B is. Okay, it's just kind of a shortcut, right? And then corollary 4.2 says there can be at most one right or one obtuse angle in a triangle. Okay, I'm gonna demonstrate this for you. Here's an obtuse angle. Okay, if I try to draw another obtuse angle, there's another obtuse angle, but that doesn't make a triangle. It's not even a closed figure. There's no way I can draw a triangle that has more than one obtuse angle, or a right triangle. There's a right angle. If I try to draw another right angle, nope, not even a closed figure. So this is just kind of basic stuff. I'm going to put there can be at most one right or obtuse angle in a triangle. Oh, sorry, you can't see that. There can be at most one right or obtuse angle in a triangle. So I'll just draw a picture of an obtuse triangle, maybe. Or a right triangle. So you can't have any more than one right or one obtuse angle. Okay, that should just be pretty basic, right? Let's go down for the last example. Again, pause that if you need to, if you didn't get all that written down. Example 3, here we go. Find the measure of each numbered angle. So I've got angle 1 that we need to solve for. I've got angle 2 over here, angle 3, and angle 4. Those are the 4 angles that I need to solve for. Okay? Again, you don't have to do it necessarily in this order. So let's do this. I am going to start with angle 1, I guess. Let's look at angle 1 over here. Okay. 52 is this angle down here in the corner, but I know that this is a right triangle, and up here it said that the acute angles of a right triangle are complementary. So if this is 90 degrees, and the whole triangle adds up to be 180 degrees, then 52 plus whatever angle 1 is has to be the other 90, right? So I can just do 90 minus 52, and that is, what, 38, I think, something like that. Check and make sure that that's right. I'm pretty sure it is. 38 degrees is what angle 1 will be, so I'm going to label him 38 degrees, okay? Then I'm going to go ahead and do angle 4, angle 4 also. This is a perfect rectangle because I have a right angle here, a right angle here, a right angle here, and even though there's not a right angle in this corner, that has to be another right angle, right? Otherwise, it wouldn't work. Okay, there's no way that can't be a right angle. So 38. Angle 1 and angle 4 add up to be 90 degrees. So if this one's 38, then this one has to be 52 again. Look at that. 52 degrees is what angle 4 is. Okay. So it kind of like has the same pattern all the way around. 52, 38, 38, 52. Okay, angle 3. Let's do him next, all right? Use a different color. If this is a right angle right here, then this other side has to also be a right angle. So here I have this right triangle again on that top part, okay? And so if this is a right angle, then this angle and this angle have to be complementary. So 52 plus whatever angle 3 is has to be added up to be 90. And that's going to be that 38 again. So angle 3 is 38 degrees. And angle 2, since that's a 90 degree angle, if we subtract 38 from 90, kind of like what we did here, it is 52. So there we go. We have 38 and 52 and 38 and 52. Okay? All right. If you need to pause, rewind, do any of that, feel free to do so. But there is section 4.1.